Welcome to the introduction to section 4.5. This is the last section that we'll cover in the textbook this quarter. This will set you up for the beginning of Math 142, which you should start with this topic at the beginning of 142, but really quickly. Okay, we'll start with a fact. The chain rule would allow us to show that the derivative with respect to x of sine of x squared is 2x times cosine of x squared. However, how do we undo that? Because every derivative fact gives us an antiderivative fact. That one tells us that the antiderivative of 2x cosine of x squared is equal to sine of x squared plus a constant. Okay, so we got to decide how to undo the chain rule. So here's our first integration technique. You'll get a bunch more in Math 142. This integration technique is called substitution, often called U substitution, but the letter really doesn't matter in this context, but we'll use U here to be consistent. So here's what we do. We're going to make a change of variables. I'll do a bunch of examples. And so our change of variables is just like when we recognize that we have to use the chain rule because we have a function inside of a function. We choose u to be a function that's living inside of a function. So in this case, I'm going to let u be x squared because it's the argument right here going into the cosine function. I'm going to take its derivative with respect to x. Du dx is 2x dx. And I'm going to operate with du and dx just like we did when we were looking at differentials. Oops, sorry. Du dx is 2x. I got one step ahead of myself there. I'm going to operate here with dx and in essence think about multiplying both sides by dx. Du is 2x dx. Now I'm going to come back to my integral. So we're trying to find the antiderivative. We know what it is, but we're trying to see how we could show it of cosine of x squared dx. Well, I'm going to rewrite this ever so slightly as the antiderivative of cosine of x squared times 2x dx. Now I'm going to come back over and try to change this entirely in terms of the variable u. And here's what I mean. This x squared, that is exactly what we called u. This 2x dx, well, I come back over here. 2x dx, another name for that is du. And now this rewrites as the antiderivative of cosine of u du. Now it says take the antiderivative of cosine with respect to the variable u. Well, we know that antiderivative. The antiderivative of cosine is sine of u plus a constant. However, we have to be careful. The original question was asked in terms of the variable x, so we better end here in terms of the variable x. So everywhere we see a u here, we're going to replace it with an x squared. So sine of x squared plus a constant. Okay, so there's u substitution in an example, or substitution. I could have used t or s or r or any variable except for x to make my substitution there. So let's see, this is, what are we really doing is we're undoing the chain rule. So there's a reminder of the chain rule. And here, we can do u substitution generally here. We let u be the inside function, which is g of x. The derivative of u with respect to x, well, that's g prime, whatever its derivative is. So that means du is g prime of x dx. And now I look here, I come back up to my integral, g prime of x dx, that's another name for du. And g of x is another name for u, and this integral then becomes the antiderivative of f prime of u du. Well, the antiderivative of f prime, that's just f of u plus a constant, which is, well, we got to answer in terms of x because that's what we were originally asked, f of g of x plus a constant. So as we would expect, the chain rule gives us a antiderivative fact as well. This antiderivative is f of g of x plus a constant. So we can generalize this. It's not really that hard to generalize our undoing of the chain rule with a substitution here. Okay, so here we go. I'm going to do some examples, but let's see, I think I have 4 examples here. And for each example, before I do anything, any calculations, I'm just going to walk through each of them and talk through the appropriate choice of u. because I think that's usually the most challenging part in these situations. Okay, so here is the antiderivative of x times 2x squared plus 1 raised to the 9th power. Okay, so we're looking for a function inside of a function, and here I see 2x squared plus 1 inside of the function raised to the 9th power. So that would be my initial choice for u. It's possible when we start u substitution we don't make the right choice, right? But we see what happens, and if we can rewrite the integral in terms of u, hopefully it becomes something a little bit simpler. Okay, here I see the antiderivative of 8 cosine of 4x dx. Okay, what's inside of a function? Well, the only thing inside of a function here is 4x. It's going in as the argument to cosine. So my choice for u here is 4x. Okay, here we have some limits of integration in these last two. I'll get to those in a minute, but let's make our choice for u first. I'm going to rewrite this. This is really the integral from 0 to pi of cosine of x squared times sine of x. Now, what's the function going into another function? Well, the only function that's going into another function here is cosine. It's going into the function raised to the 2nd power. So the initial choice for u should be cosine of x here. All right, and lastly, we have 10x to the 1/2 power over 1 plus x to the 3/2 squared. Okay, the only thing being raised to a power here, or sorry, the only thing going inside of another function here is the thing being raised to the 2nd power, and take all of it. 1 plus x to the 3/2. You might say, why not just take the x to the 3/2 part? Good question. Because the derivative of 1 is 0, so it's not going to play a role in du. So we take as much as we can as our choice for u. Okay, let's go back up now and walk through these now that we've seen that we look for the function that's inside of another function as our choice for u here. All right, so now in this example, I'm going to du is 4x is the derivative of 2x, derivative of 1 is 0, so it's 4x dx. Now, this is a little different than the example above. We have a little bit of work to do. I'm going to rewrite this. When you're first doing this, it probably makes sense to rewrite in this way, because you know the x dx is going to be part of du. And so then I look at this and say, okay, somehow I have to match this thing, x dx. And then I come back over here to where I've taken the derivative and I say, oh, if I want an x dx, I'll multiply both sides of this thing by 1/4. 1/4 times 4 is 1, so I'm left with an x dx. So I can replace this x dx then with 1/4 du. I need everything in terms of u. Well, the thing inside the parentheses here is u. So my initial rewrite of this integral looks like u to the 9th times 1/4 du. And now that's just a constant, that 1/4. So that 1/4 can actually come out in front of the integral. And so I have 1/4 the integral of u to the 9th du. You may start to do this faster and not need to move terms around, label them all as you gain some practice, but at first it doesn't hurt to do that. And so now we can take the antiderivative, that's 1/4 times u to the 10th divided by 10 plus a constant, and of course we can't finish in u, we have to go back in terms of x. So let's see, in the numerator here when I multiply I have u to the 10th. So that's 2x squared plus 1 to the 10th, and in the denominator I have 4 times 10 or 40 plus a constant. Okay, so we just showed that the antiderivative of x times 2x squared plus 1 to the 9th dx is equal to that. And if you're ever in doubt, how do you check? Take the derivative of the thing on the right-hand side, and you better get the thing that's inside the integrand or something went wrong, right? So don't be afraid to check with derivatives. All right, so let's go on to the second example here. So let's see, so du, well, the derivative of 4x is 4. It's 4 dx. So now I look up into my integral and I have an 8 dx. I see an 8 dx, so I need to multiply by 2 this time. So 2 du is 8 dx. And so we could think about rewriting this if we want as cosine of 4x times 8 dx. We just saw that this term, 8 dx, I can replace that with 2 du, and 4x gets replaced with u. So just like above, this 1/4 du, the 1/4 came out in front of the integral. I can do that again with the 2 here. So the 2 can come out in front of the integral. We rewrite it, it's the antiderivative of cosine of u du. Well, what function has antiderivative cosine, or has derivative cosine? Sorry, that is sine. So that's 2 sine of u plus a constant. But again, what variable was this original question asked in terms of? It was asked in terms of x, so we got to go back. So we get 2 sine of 4x plus a constant, and we just decided that that is the antiderivative of 8. Cosine of 4x dx. Okay. All right, so that's indefinite integrals using u substitution. Now let's look at a couple examples of definite integrals using u substitution. There's technically 2 ways to handle definite integrals. I'm going to show you one because I'm a huge proponent of it. Sometimes it takes me all quarter in 142 to convince students of this. I think the way to go here is to rewrite everything in terms of u, and that includes the limits of integration. So let's start here. So du, when we take the derivative of cosine, du is negative sine of x dx. And we look at our integral and we want to match this thing. We want to match a sine of x dx. So if we multiply both sides by -1, negative du is sine of x dx. So at this point, we can really rewrite this integral. It looks like the integral, I'm going to leave the limits off. Cosine is being played by u. Here we decided this was a negative du. And again, the negative can come out in front just like the 1/4 and the 2 did above. It's just a constant -1 being multiplied. The cosine of x squared is u squared, and sine of x dx is du. Okay, antiderivative we can definitely handle, but the limits that we were given were in terms of x, and I want to change the limits to u. And so I'll do that over here, and then we can finish this antiderivative all in terms of the variable u without ever having to go back to x. Change limits to u. What do I mean by that? Well, my first lower limit of integration is when x is equal to 0. So when x is equal to 0, u is going to equal cosine of 0, which is 1. So my new lower limit, when x was 0, u is 1, so my new lower limit of integration is 1. Upper limit of integration, when x is pi, u is cosine of pi. See, what is cosine of pi is -1. So when x is pi, u is cosine of pi, so my new upper limit of integration is -1. Now I remember that if I multiply the integral by a negative sign, I can flip the limits of integration. So this negative right here gives me a positive, and I flip the limits of integration, -1 to 1, u squared du. You don't have to do that. You could continue as is. You just got to be careful with that negative sign when you evaluate the integral. Okay, so now we're done. We've changed our limits of integration from x to u, which is nice because now we can finish. We're all in terms of u. We don't have to go back to x. We don't have to worry about bringing the correct limits back. We can just evaluate this thing. This is u cubed over 3 evaluated from -1 to 1, which is 1/3 minus -1/3, or 2/3. So we just decided that the value of this integral from 0 to pi of cosine squared sine of x is 2/3. So that's the area between that function and the x-axis on the interval from 0 to pi. Okay, one more example here, and I'll do the same thing with the limits of integration. I really think it's the way to go when we are doing substitution. Okay, so first we'll take derivatives. So du is the 3/2 comes down, 3/2 x to the 1/2. Okay, so then I look up at my integral, dx, and I say, do I have an x to the 1/2 power? I sure do, but I have 10 copies of it. So what do I have to multiply 3/2 by to get 10? I think that number is, let's see, if I divide by 3, I'll have a half. So I think it's 20 over 3 would do the job. So 20 over 3 times du. Let's see, that's going to give me 60 over 6, which is perfect. That's 10x to the 1/2 dx. So I multiplied both sides of that equality by 20/3. Now let's rewrite this integral so we can see it. So this is, I'll leave the limits of integration off again, and I'm going to rewrite this. It's really 1 over 1 plus x to the 3/2 squared times 10x to the 1/2 dx. Okay, we can handle this. We just figured out what this thing is. It's 20/3 du, and we know what this thing is. It's just u. So now we just need to change our limits. Change limits to u. So when x is 0, that's our lower limit of integration. U is going to be 1. It's annoying, sorry. 1 plus 0 to the 3/2, which is 0. So u is just going to be 1. So our new lower limit of integration is 1. When x is 1, u is going to equal 1 plus 1 to the 3/2. But 1 to the 3/2 is 1, so our new upper limit of integration is 2. All right, perfect. We can simplify this thing, make it look a little bit neater, and just finish in terms of the variable u since we changed our limits of integration. So 20/3 again is a constant, just like in all the examples above. So it's being multiplied so it can come out in front of the integral. And it looks like the integral from 1 to 2 of 1 over u squared du. Perfect, we can handle this one. This is 20/3, the integral from 1 to 2 of u to the -2 du, which is 20/3 times, we have to be careful here with the multiplication, u to the -2, add 1 is u to the -1, divide, so negative u to the -1, evaluated from 1 to 2. over 3 times negative u to the -1 is -1 over u. So when I evaluate that at 2, I get -1/2. Minus a minus gives me a plus, and when I evaluate that at 1, I get 1. So that thing in parentheses looks like 1/2 times 20/3, or 10/3 square units. I'll leave the square units off. I don't want you to be confused with the u above because they're not related. So it's 10/3. So the area right here between this function and the x-axis is 10/3. Okay, there's u substitution. Try to take that information and work on the class activity for section 4.5.